Κυρίες και κύριοι, καλησπέρα σας. Σας καλωσορίζουμε στην τελετή έναρξης του Συμποσίου 7th International Interdisciplinary Symposium on Chaos and Complex Systems. Η τελετή θα ξεκινήσει με την ανάγνωση του χαιρετισμού του κυρίου Πρίτανη, του Εθνικού και Καποδιστριακού Πανεπιστημίου Αθηνών, καθηγητή Γεράσιμου Σιάσου. Ladies and gentlemen, good evening. We welcome you to the National and Kapodistrian University of Athens. The opening ceremony of the symposium begins with a reading of the welcoming address by the Rector of the National and Kapodistrian University of Athens, Professor Gerasimos Chiassos. A translation in English of the Rector's address has been given to you previously. Αθήνα, 19 Ιουνίου 2026. Με ιδιαίτερη χαρά χαιρετίζω την έναρξη του 7th International Interdisciplinary Symposium on Chaos and Complex Systems, ενός διεθνούς επιστημονικού θεσμού που έχει πλέον καθιερωθεί ως σημείο συνάντησης επιστημόνων από διαφορετικά γνωστικά πεδία. Η επιλογή του Πανεπιστημίου Αθηνών για τη διοργάνωση αυτού του σημαντικού συμποσίου έχει ιδιαίτερο συμβολισμό. Στην πόλη της Αθήνας, η οποία συνδέεται ιστορικά με τη γέννηση της φιλοσοφικής σκέψης, της επιστημονικής αναζήτησης και του ορθού λόγου, επιστήμονες από ολόκληρο τον κόσμο συναντώνται σήμερα για να διερευνήσουν ένα από τα πλέον δυναμικά και γοητευτικά πεδία της σύγχρονης επιστήμης, την πολυπλοκότητα και το χάος. Το φετινό θέμα, Innovation and Complexity, from Physics to Medicine and Pharmaceutics, αναδεικνύει με ιδιαίτερα εύστοχο τρόπο τη σύνδεση της θεμελιώδους επιστημονικής έρευνας με τις εφαρμογές που επηρεάζουν άμεσα τη ζωή των ανθρώπων. Η φυσική, τα μαθηματικά, η μηχανική, η βιολογία, η ιατρική, η φαρμακευτική, η επιστήμη των υπολογιστών και η τεχνητή νοημοσύνη δεν λειτουργούν πλέον ως απομονωμένα πεδία. Αντιθέτως, συγκροτούν ένα ενιαίο οικοσύστημα γνώσης μέσα στο οποίο γεννώνται οι μεγάλες καινοτομίες του 21ου αιώνα. Ως προς το πρώτο και μεγαλύτερο πανεπιστήμιο της χώρας, επενδύουμε διαχρονικά στη συνεργασία μεταξύ διαφορετικών επιστημονικών πεδίων, στη διεθνή δικτύωση και στην παραγωγή έρευνας με ουσιαστικό κοινωνικό αποτύπωμα. Η φιλοξενία του παρόντος συμποσίου αποτελεί μία ακόμη απόδειξη της προσήλωσης του Ιδρύματός μας στην αριστεία, την εξωστρέφεια και τη διεθνή επιστημονική συνεργασία. Η παρουσία κορυφαίων επιστημόνων διεθνούς κύρους επιβεβαιώνει τη σημασία του συνεδρίου και το υψηλό επιστημονικό του επίπεδο. Αποτελεί ιδιαίτερη τιμή για το Πανεπιστήμιό μας η συμμετοχή του Προέδρου της Ευρωπαϊκής Ακαδημίας Επιστημών και Τεχνών, καθηγητή κυρίου Κλάους Μάνσα, ενός από τους σημαντικότερους εκπροσώπους της σύγχρονης επιστήμης της πολυπλοκότητας διεθνώς. Θα ήθελα στο σημείο αυτό να εκφράσω τις θερμές μου ευχαριστίες προς τους συμπροέδρους του συνεδρίου, τους διακεκριμένους καθηγητές, κύριο Σταύρο Σταυρινίδη, κύριο Μεχμέτο Ζέ και τον κύριο Κωνσταντίνο Δεμέτζο για την πρωτοβουλία και την άρτια επιστημονική οργάνωση αυτής της διεθνούς συνάντησης. Εκ μέρους των Βρετανικών Αρχών εύχομαι κάθε επιτυχία στις εργασίες του Συμποσίου και είμαι βέβαιος ότι οι συζητήσεις και τα συμπεράσματά του θα συμβάλλουν ουσιαστικά στην πρόοδο της επιστήμης, της καινοτομίας και της διεθνούς ακαδημαϊκής συνεργασίας. Με εκτίμηση, ο πρίτανης του Εθνικού και Καποδιστριακού Πανεπιστημίου Αθηνών, καθηγητής Γεράσιμος Χιάσος. Ακολουθεί η παρουσίαση του συνεδρίου εκ μέρους των συμπροέδρων από τον καθηγητή του Δημοκριτείου Πανεπιστημίου Θράκης, κύριο Σταύρο Σταυρινίδη. Welcoming introduction to the conference on behalf of the co-chairs by Professor of Democritus University of Thrace, Professor Stavros Stavrinidis.
President of the European Academy of Sciences and Arts, Professor Mainzer, esteemed co-chairs, Professor Mehmet Özer, Professor Kostas Demetsos, esteemed invited speakers, honored keynote speakers, distinguished colleagues, researchers, guests, and explorers of complexity, ladies and gentlemen. Welcome to the 7th International Interdisciplinary Symposium on Chaos and Complex Systems, what we call as an acronym SCCS 2026. Last year, we gathered at a geographical crossroads where two continents meet, the queen of the cities, Polis, as both Mehmet and I are calling her. This year, it is my profound privilege to welcome you to Athens, a city that is not only the cradle of democracy, Western philosophy, and classical science, but a setting that embodies the very essence of emergent order from historical chaos. As we stand here at the National Capodestrian University of Athens, we walk the same ground where ancient philosophers first pondered the fundamental fabric of reality. It was Hesiod who millennia ago postulated that chaos was primordial void from which the cosmos, order, and all the creation emerged. Today, we return to this historic birthplace not with mythological awe, but with the rigorous tools of modern nonlinear dynamics, network theory, and computational intelligence. We are here to prove that within the seemingly unpredictable, there lies an elegant, intricate geometry waiting to be decoded. Over these 3 days that SCCS 2026 will last, researchers hailing from about 20 countries will join forces. Together, we form an intellectual ecosystem that transcends borders, languages, and traditional academic silos. The trajectory of the SCCS Symposia has always mirrored the acceleration of science itself. This year's edition marks a monumental leap forward. We find ourselves living through a technological revolution where the boundaries between physical systems, biological frameworks, and digital realities are permanently blurring. At the absolute center of this, I could say at the absolute center of this convergence, artificial intelligence stands. While traditional AI relies on rigid linear logic, the next generation of AI, the algorithms that will truly change the world, draws inspiration from the unpredictable nature of biological systems, reservoir computing, and physics-informed neural networks. We are realizing that to build machines that think, adapt, and learn like the human brain, we cannot rely on linear deterministic predictability. We must embrace the edge of chaos. This symbiosis between chaos theory and artificial intelligence is reshaping predictive modeling, data science, and autonomous systems. As practitioners of complexity, I would say as artists of complexity, we are uniquely positioned to contribute to this revolution, and I would dare to say to guide this revolution, ensuring that emergent AI systems remain resilient, secure, and understandable. Our scientific committee has helped us to curate a rich, robust, and highly interdisciplinary program. Over the course of this symposium, our plenary and keynote sessions, workshops, and oral presentations will navigate across several critical pillars as the nonlinear dynamics and foundations, diving deep into chaotic synchronization, fractional dynamical systems, and the control mechanisms that govern everything from the macro scale of the universe to microscale and nanoscale phenomena, physics of complex systems, investigating the bedrock principles of statistical mechanics, multiscale modeling, and the enduring beauty of fractals, solitons, and entropy. Network theory and structural resilience, examining the vulnerability, structural complexity, and topological dynamics of physical, biological, and informational networks. AI and machine learning in complex systems, exploring the frontiers of physics-informed networks, reservoir computing, and how chaos-inspired learning algorithms can solve previously intractable problems. Complex adaptive systems and self-organization, unpacking how decentralized autonomous components give rise to collective intelligence, swarm behavior, and spontaneous pattern formation. Complexity across applied sciences and engineering, broadening our horizons into climate modeling, sustainability, astronomy, hardware security, physical unclonable functions, and chaotic cryptography. Socioeconomic complexity and econophysics, bridging the gap between equations and human behavior by dissecting financial market crises, social network dynamics, and game theory under deep uncertainty. Biomedicine and pharmaceutics, I keep it last, witnessing how nonlinear modeling, revolutionizing drug delivery, identifying critical thresholds in physiology, and mapping complex biological pathways. This last pillar is the central pillar of this year's Symposium edition, innovation and complexity from physics to medicine and pharmaceutics. Furthermore, following the conclusion of our time together, the cutting-edge insights shared here will be preserved and shared globally. To these directions, accepted full papers will be published in the prestigious Springer Nature Proceedings in Complexity, ensuring that the ripples of our discussions here in Athens will expand outward into the broader scientific community. Ladies and gentlemen, the study of complexity is more than a scientific discipline. It is a worldview. It requires a distinct kind of intellectual humility and courage. It forces us to admit that the universe cannot be neatly compartmentalized or reduced to isolated linear systems or linear equations. To solve the grand challenges of our era, whether they are global climate shifts, economic instabilities, cybersecurity vulnerabilities, or the ethical governance of autonomous AI, we must think synthetically. We must look across the boundaries of our specific domains. A breakthrough in a physics lab today could be the key to understanding a financial crash tomorrow. A pattern discovered by a biologist today might unlock the next leap in machine learning and new algorithms tomorrow. This symposium is designed specifically to be that spark. I urge you over the next 3 days to step outside of your comfort zones, attend sessions outside your primary domain, challenge your own foundational assumptions, ask difficult and unconventional questions. But most importantly, use the informal spaces of coffee breaks and our Mediterranean cultural environment to build bridges, form new international collaborations, and cultivate lifelong friendships. To conclude, I would like to express my deepest gratitude to the organizing committee and the production team of Nufio Company, our host institution, the National and Capodistrian University of Athens, Demokritos University of Thrace, my university, Istanbul Kultur University, Professor Ozer's University, the Hellenic Pharmaceutical Society, where Professor Demedjos, next to being a professor here at the University of Athens, is also the president of the society. Their tireless, behind-the-scenes efforts have transformed this vision into reality. I also want to express our gratitude to the European Academy of Sciences and Arts for endorsing this conference series as well. On behalf of my co-chairs, Professor Ozer and Professor Demedjos, it is my distinct honor to declare the 7th International Interdisciplinary Chaos Symposium officially open. May the spirit of Athens inspire your minds, may your data fill your attractors, and may our collective efforts push the boundaries of human knowledge. Thank you very much, and welcome to SSC 2026. Thank you so much. Now I invite the President of the European Academy of Sciences and Arts, Professor Klaus Mainzer, to deliver the symposium's opening talk, of course, after your presentation. Thank you.
Θα ακολουθήσει βιντεοσκοπημένος χαιρετισμός από τον Υφυπουργό Παιδείας, Θρησκευμάτων και Αθλητισμού, πρώην πρίτανη του Αριστοτελείου Πανεπιστημίου Θεσσαλονίκης, καθηγητή Νικόλαο Παπαϊωάννου. Recorded address by the Deputy Minister of the Ministry of Education, Religious Affairs and Sports and former Rector of the Aristotle University of Thessaloniki, Professor Nikolaos Papaiωάννου.
Distinguished President of the European Academy of Sciences and Arts, Professor Klaus Mainzer. Distinguished co-chairs, Professor Stavrinidis, Professor Ozer, and Professor Demedjos. Esteemed members of the scientific community, ladies and gentlemen, good evening. Although I am unable to be with you in person today, I am delighted to address the opening of the 7th International Interdisciplinary Symposium on House and Complex Systems. I want to warmly congratulate the organizers for bringing together in Athens an outstanding international community of researchers and scholars dedicated to advancing knowledge in one of the most dynamic and influential fields of contemporary science. I am particularly pleased to welcome Professor Klaus Mainzer, President of the European Academy of Science and Arts, whose pioneering work has significantly advanced our understanding of complexity and its implications of the modern world. The study of house and complex system has evolved far beyond the boundaries of a single discipline. Today, It provides valuable insights into challenges ranging from artificial intelligence and technological innovation to biological, social, and economical systems. It reminds us that the most important questions of our time require collaboration across scientific fields and across national borders. This interdisciplinary spirit is also at the heart of our vision for modern higher education in Greece. Universities are increasingly called upon to foster research environments where diverse disciplines interact, innovation flourishing, and new knowledge emerges through cooperation. Particularly timely in the Symposium's focus on artificial intelligence. As AI increasingly influences research, education, industry, and public life, it becomes essential to understand not only the capabilities of intelligent systems, but also their broader implication for society. Scientific progress must always be accompanied for responsibility, transparency, and ethical reflection. In this regard, the dialogue between complexity science, technology, and the humanities is more important than ever. It is especially fitting that these discussions take place in Athens, a city where scientific inquiry and philosophical thought have shaped intellectual progress for centuries. By bringing together experts from different disciplines and countries, this symposium contributes to a global dialogue that is vital for the future of science and society. I wish you every success, fruitful discussions, and new collaborations that will contribute to scientific progress and innovations. May this conference be truly inspiring for all of you. Thank you so much.
Ανάγνωση του χαιρετισμού του πρίτανη του Δημοκριτείου Πανεπιστημίου Θράκης, καθηγητή Φώτιου Μάρη. Reading of the address by the Rector of Democritus University of Thrace, Professor Photios Maris.
Dear President of the European Academy of Sciences and Arts, dear organizers, ladies and gentlemen, following Professor Stavrinidis' invitation and on behalf of Democritus University of Thrace academic community, it is a profound honor and pleasure to welcome all distinguished researchers, scholars, and participants to the 7th International Interdisciplinary Symposium on Chaos and Complex Systems. Our institution, Democritus University of Thrace, deeply committed to pioneering academic excellence and fostering international and scientific dialogue, takes great pride in endorsing this prestigious event. Our commitment to cutting-edge research is exemplified by the activities of our academics in all sciences domains, which serve as a cornerstone for investigating the fundamental principles that govern complex systems in nature, society, and technology. These activities hold a special significance for us as they closely align with the vision and research mandates of our newly established Complexity Institute. The Institute's dedication to deciphering nonlinear dynamics emergent behaviors, and the intricate networks of complex systems, perfectly mirrors the core ethos of this Chaos Symposium, creating a powerful synergy for advancing the frontiers of modern science. In an era where contemporary global challenges demand multifaceted and interdisciplinary approaches, the study of chaos and complexity serves as a vital bridge connecting diverse scientific fields. I am confident that the groundbreaking research, vibrant discussions, and collaborative ideas sparked during this symposium will not only push the boundaries of theoretical understanding, but also inspire innovative practical applications. I wish you all a highly productive, inspiring, and successful conference. Professor Fotios Maris, Rector of Democritus University of Thrace.
Κεντρική ομιλία από τον Πρόεδρο της Ευρωπαϊκής Ακαδημίας Επιστημών και Τεχνών, Senior Excellency Faculty, Technische Universität München, and Karl Friedrich von Weizsäcker Center, Universität Tübingen, καθηγητή Klaus Manzer. Opening lecture by the President of the European Academy of Sciences and Arts, Professor Klaus Manzer, entitled From Complex Systems and Non-Linear Dynamics to Neuromorphic Systems and Physical Artificial Intelligence.
Excellencies and magnificences are not here, but we heard their important and kind and nice words. Dear organizers, dear colleagues, ladies and gentlemen, I had already a talk on Wednesday here in this hall, and so I feel already at home. But this talk was on science policy and the Greek heritage. And let me first bring the greetings in an official function here of the European Academy to this remarkable and important conference. Now, my contribution as a scientist, as an opening lecture for the conference, from complex systems and nonlinear dynamics to neuromorphic systems and physical AI. And that is, in my case, on a long-term engagement in these topics, starting in the early 90s with the books on complexity, then artificial intelligence, quantum computing, and neuromorphic computing. And on that background, I will start with some basics of complex dynamical systems. And this morning already the conference started and we heard some important aspects already. And on this basis, I will extend the topic to what is nowadays discussed as AI. But not only to machine learning, that is what most people know, but also to physical AI, to neuromorphic AI and quantum AI. And I will end with remarks on challenges of complexity and hybrid AI. Now let's start with the basics of complex dynamical systems. Now, complex systems you find everywhere in the natural evolution, starting with the cell as a complex system of interacting molecules, and on the next level, an organ as a complex system of interacting cells, and on the next level in medicine, a complex organism of interacting organs, and then in population dynamics, a population as a complex system of interacting organisms, and then finally an ecological system as a complex system of interacting populations. And all these in all these examples, from a physical point of view, we consider so-called open systems. That means systems which are in a permanent interaction with their environment by matter exchange, by energy exchange, or information. And what we observe is that at critical points of this exchange, the so-called critical values of control parameters, we can observe the spontaneous emergence of structure and even of chaos. And that can be mathematized. And here it is illustrated for different domains. On the left, let's start with chemistry. A famous traditional example, the Belousov-Jabotinsky reaction. That is a chemical reaction, and you can observe that in dependence of the input from outside, at a critical point, as I mentioned before, the sudden emergence of these patterns here, macroscopic patterns of pulsing ring waves, and that can be mathematized by this equation which you see above. The state of a molecule is represented by a variable x with three spatial coordinates alpha, beta, gamma, and f means the transition function for the state of the molecule, and then the interaction here in the formula is represented by this coupling term depending on a certain diffusion coefficient d. And then all is considered as a time-depending dynamics represented by a difference equation or differential equation. And the second example, besides the Belousov-Jabotinsky reaction, that's the red one on the left, you see a completely different domain, namely the brain. And here the elements are the neurons, and the interactions are synapses and new chemical signals. And that can also describe with the same kind of equation which I explained before. In this case, it was for the first time done by two Nobel Prize winners in medicine. Remarkable, because it is mathematics. They were a Nobel Prize winner in mathematics, and they described it for the first time, the Huxley-Hodgkin equations. And the next picture, that is the emergence of patterns on the shell of snails, or the right picture with these wonderful pattern on the wings of a butterfly. And that can be described by the same kind of equation by Gira and Meinhardt. Now, anyway, you get a kind of universal reaction diffusion equation to describe and to explain the emergence of patterns in nature. And that is a scheme, a geometrical scheme to illustrate what is going on. A spatial lattice consists here of identical cells located at these grid points and changing their states by local reaction diffusion. Now, the question is, what is the cause? What is the cause for the emergence of these complex structures in nature? And the cause is that these kind of elements are what we call locally active. And that can be chemical elements or organic cells like the neurons in the brain or transistors in the technical network. And the essential feature which is meant by local activity is the feature of amplification. They can amplify small input signals into high power output signals at the expense of energy support. And that can be mathematical described by an integral. You know, perhaps if you are not scientists from school, integral means summing up here these small inputs. That is a rigorous definition, but in order to apply it in the different domains, you need criteria. And this integral, defining local activity, can be described equivalently by a kind of complexity function or by criteria in the equations which I mentioned before, the Jacobian matrix of the reaction diffusion equations. I will not go in these mathematical details. The point is, with this formal equipment, you can calculate all these formations and sometimes miraculous emergence of patterns which I mentioned before. And that is a very prominent example, our brain as a complex system. There are also local active cells, the neurons, and here you see pattern formation in the brain, here in yellow and red. These are the so-called PET pictures. PET, P-E-T, means positron emission tomography. And this kind of illustration of activity in the brain was also done for the first by a Nobel Prize winner in medicine, Kendall. And the amazing feature here is that these pattern formation, which are described by the physicians and the neurologists, is correlated by pattern recognition. That means by perceptions, even by emotions, thoughts, and consciousness. So here is a correlation between the natural sciences, brain research, and on the other side, psychology. Now, that can be simulated on the computer. Here we use not the Hodgkin-Huxley equation, but a simplified version of the Fitzhugh-Nagumo equations, which only depend on two variables here, V1 and V2 for the voltage, measuring the voltage, or by a variable for the recovery state of the neuron. And above you see the two-dimensional patterns, and you can also consider the time-depending development at the time axis in a time series analysis, and then you get these oscillation patterns. And then there is a very remarkable, and that was new in the scientific community, a new insight, namely the so-called edge of chaos. And the edge of chaos means, roughly speaking, it's sometimes understood a little bit contrary to our intuition, that even cells which are stable can be active and can initiate the pattern formation. In general, people believed, even famous scientists, nonlinearity is sufficient, perhaps with instability, but here stable cells can become active. But the essential request is the local activity, which I mentioned before. And remember, local activity means the feature for self-amplification, which I mentioned before. And that goes back to a deep discussion, even in mathematics. Here, not a Nobel Prize winner, but a Fields Medal winner is involved, and Smale from UC Berkeley. And actually, this discussion goes back much earlier to Alan Turing. Alan Turing is known as computer scientist, but in the end of his life, he was also engaged in pattern formation in chemical morphogenesis. And here on the right, you see the emergence of a chaos attractor, typical for the edge of chaos. Now, the situation is, on the left, in nature, in the complex systems, the emergence of new structures explained by the principle of local activity. And then I mentioned that the brain is a special system with not only pattern formation, but also pattern recognition. And that can be simulated on a computer, and that will be considered now in the next part of my talk. But before I come to AI with machine learning, we have to be aware what a computer is exactly. And later on in my talk, you will understand why I underline these logical, mathematical understanding of a computer. And that goes back to the midst of the 30s by a famous paper of Alan Turing, the British computer pioneer, logician, and mathematician. And he, for the first time, defined rigorously what a digital algorithm is, what a digital computer is. That is his concept of a so-called Turing machine. I will not go here in the details. The essential point, which I will need later on, is the strict separation of memory and the processor. And in that time, of his time, in the 30s, that was the time of typewriters, and therefore he illustrated it in this way. You see there an unlimited tape. The tape represents the memory. It is divided into several squares, and there are symbols, numbers, and letters which can be deleted or can be printed, and that is done by a processor. That is this yellow unit here. And later on, it turned out that this simple concept is, in a mathematical strict sense, equivalent to all kinds of digital algorithms which were introduced later on, and the so-called church thesis. And technically, for the first time, that was 1936, it was realized in Germany by Konrad Zuse, 1941, the first technical computer with the strict separation of memory and the processor, and 4 or 5 years later by John von Neumann in the US. This kind of architecture is until today called the von Neumann architecture, and I will come to that later on again. But what I also want to highlight here, that just from the beginning with the paper of Turing, the concept of a digital computer, and that means a supercomputer here in Athens and Munich and elsewhere, that means your smartphone, that means your laptop, is connected with logical mathematical limit. And that was famous also in the paper of Turing, the famous undecidability of the so-called halting problem. And that means, roughly speaking, that there is no general algorithm to decide whether an arbitrary Turing machine with an arbitrary input will stop after finite steps or not. Roughly speaking, that means it is not possible to have a general algorithm which can solve anything. And that, I think, is amazing because it is a logical limit. You cannot improve it by technology and perhaps hope, oh, in the next years we will do it. No, because the assumption you can solve this problem would contradict to a definition of an, in principle, non-computable real number. You can say, oh my goodness, that is a very abstract limit of digital computing. But later on it turned out that this problem is mathematically equivalent to real mathematical problems. In 1970, a Russian mathematician, Matyashevich, in Leningrad, came up with a proof that the halting problem is equivalent to famous, until that time, unsolvable problems in mathematics. The so-called Hilbert tensor problem. Hilbert on the right, perhaps you know him from Göttingen, and this problem was until that time believed to be not solvable, and or it is solvable, nobody knows. It concerns equations with integers, the so-called Diophantine equations. And it is equivalent to the halting problem. The halting problem is not decidable. Also, this problem is in principle, in mathematics, logically not decidable. Now, anyway, please keep it in mind. I will come to that later on. On this basis, in 1950, also Turing presented the first definition of AI. That is for a famous Turing test, the simulation game, which is illustrated here intuitively. That means that a system, for example, a Turing machine, should be called intelligent if in its reactions and solutions it cannot be distinguished from a human by a human interrogator here on the left, communicating with this human and the system hidden perhaps behind a wall. And in that sense of the simulation game, now in machine learning, we will try to simulate the human brain. These are the so-called neural networks. And you see here some simplified graphs of a neural network. These are the rings, represent the neurons, which I mentioned before, the arrows, the synaptic interactions. And then you must imagine that in the graph, these arrows are weighted by numbers. The numbers indicate the new chemical intensity of these signals. And then local activity principle, again. It is said, Hebb's law, for example, that this neuron becomes active, it fires or generates a bit whatsoever, if the sum of the neighbored input, here these arrows, are larger than a certain threshold level. And by that you get a sequence of signals which is led through the architecture here in the midst, and the architecture of the neural network is divided here in several layers, and that is quite similar to the neocortex of the human brain. The human brain, as far as I know, we have 5 layers. And these sequences of signals are triggered by learning algorithms. We can distinguish different kinds, which are mentioned there. Supervised learning means that at first you train the system with a certain pattern, perhaps with a photo, and then the system is able to recognize this photo among a huge number of other perceived photos by comparison, perhaps the pixels. And then non-supervised learning means the system is able spontaneously to detect similarities of data, and according to these criteria, it is able to classify in an automated way this kind of data set. And reinforcement learning is very interesting. You all know reinforcement learning. It means that the system is able to improve its problem-solving strategy by rewards from outside. Why do you know that? I suppose you all have used ChatGPT, and you know if you are not satisfied with the answer, then with respect to your critics, the system is able to offer improved answer. And then deep learning only relates to the depth of the system. That means to the number of layers. For example, here in the first layer, that's quite similar. Here 4 layers, neocortex 5, and the procedure is quite similar. here on the first layer only colored pixels are distinguished, and then they are connected as edges and corners, and then partial faces, and then the whole faces. In principle, that's all. That's machine learning. Machine learning, learning algorithm, pattern recognition in a huge set of data. But nowadays, these networks are not as simple as I illustrated before. There are not only 5, like in the neocortex, 5 layers, they are hundreds, thousands of layers in the neural networks which are applied, for example, in industry nowadays. There are millions of neurons, there are billions of synaptic weights, and that is mathematically represented here on the left with a network function depending on an input x, and theta means the distribution of all these millions or billions of synaptic weights. And in all these applications, in industry, in science, everywhere, in machine learning, always the same situation. Very simple. You try to train such a system, and training means changing the synaptic weights in order to approximate a certain target. And the target means, for example, a pattern, which should be recognized and is represented here by F on the right of these formulas, the target function, representing the pattern which should be recognized. And now that is a message which I underline in my talk. In all these amazing and crazy applications nowadays in AI, on the basis there are fundamental mathematical laws or physical laws. And in this case, there is a law, a theorem, a mathematical theorem, which is called the universal approximation theorem. That was, by the way, already mathematically rigorously proved in the end of the 80s. It's amazing. That's all. That's machine learning. But it says that if there is a target function which at least must be continuous, then it is mathematically guaranteed that there is such a network function which can approximate this target function with arbitrary accuracy. But that's typical sometimes for mathematics. They come up with nice existent theorems, but that's all. Of course, in order to apply these networks, that depends on the engineering of the engineers and physicists and so on, who must have computer scientists, who must have nice ideas for the concrete parameters to apply these kind of networks. Now, sometimes the picture here is illustrating that, especially in the newspapers, these networks are criticized. People say, the journalists say, oh, that's a black box. Nobody knows what is exactly going on in interaction of millions of elements. From a physical point of view, I can only say, don't worry, because these kind of complex systems are well known in physics since over 100 years. Thermodynamics, a liquid, a gas, is a complex system of millions of interacting molecules. And we have the mathematics since Gibbs and Ludwig Boltzmann, statistical mechanics, which is describing that. Now, that is illustrated here, the interacting molecules by energetic interactions, and then in a gas we can observe annealing processes, phase transitions, which mathematically can be described by gradient descent rules, and all that is well known since long time in physics. Now the idea was to use this formalism and to replace the neurons, the molecules by neurons, and the energetic interaction by synaptic interaction, and the phase transitions by learning algorithm. And we are in statistical mechanics and therefore stochastic learning algorithms in order to realize certain target function. And by that, nowadays, general problem is to solve optimization problems, which is illustrated here. You see the landscape of such a thermodynamical system or a big neural network. You can illustrate the state of the system by a ball which is running up and down here, this landscape, and there are valleys, more or less deep valleys, representing the minima of kind of problem-solving solution. And of course, we aim at the global minimum. That means the deepest valley here. For example, here in Athens, you want to have homogeneous traffic everywhere. That would be such a kind of global minimum. And these are the typical applications of statistical machine learning nowadays. And on the right, you see highlighted the people who for the first time recognized or became aware that neural networks are deeply rooted in laws of physics, and therefore 2 years ago, the Nobel Prizes, the Nobel Prizes were given to AI researchers, the Nobel Prizes of Physics. I highlight Fields Medal and Nobel Prizes in order to underline or to illustrate how deep this kind of research is rooted in a general trend nowadays of research. You can ask, is that all? Is human intelligence only statistical optimization, collecting of data? Of course not. Remember the development of science. Galilei or Newton, they had very few data of the universe, but nevertheless, they had ingenious insight in laws, in the fundamental laws, causal laws of nature, and they expressed it by mathematical equations. And that leads me now to a new tendency in AI nowadays, because everywhere is talking about machine learning. No, machine learning must be extended by causal laws and physical models. The knowledge at first of the physicists, that is illustrated here. Physical laws enable approximations which do not only statistically optimize, as I mentioned before, data masses, but consider physical knowledge, theories, and laws. For example, here, consider the famous Navier-Stokes equations, high nonlinear equations in mathematics. And the idea is to use as framework these laws in order to get better result for the only statistical optimization of machine learning. That means extending the neural networks with physical laws. That is nowadays called physical AI. And that is illustrated here in the picture. In the first block on the left, you see a neural network. The neural network, as I was, it's machine learning. That means optimizing the data, measure data, but then the result of this optimization process is compared with the given solutions of the laws, representing here in mathematical equations. That may be the reaction diffusion equations, which I mentioned before. But in medicine, for example, that can be the neural network, which is optimizing the measured data of your heart, but then it is compared with laws in medical physics, for example. the laws of dynamics of the blood pressure in the vessels, for examples, in order to minimize the difference between the solutions of the law with the measured data in order to get better, more precise results. Or the next application here is civil engineering. There's a bridge. In Germany especially, we have now the problems with a lot of damaged bridge. And you can, of course, with statistical mechanics, optimize the measured data of a bridge. But then a bridge is also a physical object. There are laws, the laws of statics, the laws of material sciences, and so the measured data and statistically optimized data should be compared with the given solutions of the laws, of the equations, in order to minimize these differences. There is some difference function there, the so-called loss function, which must be minimized in that way in order to get better results. Now, here in general, it is illustrated. Machine learning is not sufficient. That's only statistics. And then it must be extended. That means correlated, correlation-based AI, that means statistical AI. It must be extended by causal AI. Causal AI means that you can trace and explain exactly what's happening at every step in the dynamics with respect to the known laws. It's sometimes called physics-informed neural network or physics-informed machine learning. And that is not only interesting for the natural sciences. I think we have to extend this approach also in practical issues, and that will also be considered here in the conference, the socio-technical systems. That means AI is not only ChatGPT here on the left, but it must be extended also for the physical infrastructure. Some of you already have nice cars and can communicate with the car. That means the AI is integrated into the physical objects here in a car by sensors or a robot or aircraft. For example, nowadays drones. Drones is physical AI, not ChatGPT and statistical blah, blah, blah. It is integrated into the physical infrastructure, or the picture here with the skyscraper. That means even in urban structures, AI is integrated, physical AI. Now all that is fine, nice perspectives for the future, but anyway, we are running with this kind of AI in deep problems. In deep problems with respect to the needed energy. And that leads me now to next application of AI, namely neuromorphic AI, neuromorphic computing, which is also in the center here in this conference. Now the reason is the following, and now I come back to the beginning of my talk with Turing and with the von Neumann architecture. Digital computing, more or less, is still based on the von Neumann architecture. That is illustrated here on the left. You remember the strict separation between memory and processor. Here is CPU. Nowadays we have GPU and NVIDIA. That doesn't matter. It's this kind of architecture. And it needs a lot of energy and time to transfer the bits between processor and memory. And the increasing mass of data must be pressed through this von Neumann architecture. And that is sometimes called the von Neumann bottleneck. Quite contrary to the human brain. The human brain, unbelievable efficient. Do you know the what? which are needed here in the brain. As far as we know, 20 watt, it's a small lamp with all these amazing abilities of our human intelligence. And one of the main reasons is the completely different architecture. It is, as we already heard, it is a network. It is a network and no strict separation in the von Neumann sense between processor and memory. Each synapse in the living brain, can integrate both features, processor and memory. And there is not only one synapse, there are millions of synapses. So in the living brain, there is no danger of von Neumann bottleneck. And now you can say, okay, neural networks are already used in the machine learning approach, but there it is only a simulation on the classical digital computer, and that doesn't help. It needs a lot of energy again. Now the question is, can we do that in hardware? Perhaps not in wetware like living tissues, but can we do that in hardware? And the answer is yes, we can. 1971, Leon Schuer, who is later on discussed in our short colloquium, Leon Schuer came up with a theoretical suggestion which was called memristor. And that means a kind of transistor which integrates memory, the word memristor, and resistor. That means it is a nice candidate for a technical mimicking unit for the synapse. And you remember the living synapse can also both. And that is illustrated here on the left with these array here on the left. That means the grid. In the midst there is a graph which illustrates the situation. From the left, the input voltage, and then output is current. And at the grid points, you find the symbols for the memristors, which replace in the neurobiological grid of Hodgkin and Huxley the synaptical weight. And then by energy efficient parallel analog in memory computation of this vector matrix product, which is a mathematical representation of this grid, you can avoid the von Neumann bottleneck. That is the first message here, and then it reduces the energy consumption. Now, if the input and the output here, voltage and current, is proportional, then you get the well-known law, which we all know from school, Ohm's law. There is a proportionality factor that is resistance, and that is a linear law, of course. And therefore, in the coordinate system there on the right, with current and voltage, it would be represented by a straight line. But what we want to have is this memory feature. And are there materials, we want to construct it, not only to model it, are there materials which can do that? Yes, there are first materials which can have this feature of memory. For example, titanium dioxide is able to do that. If it is treated by charge, then it can generate memorial, so to say, memorial states. That means the system can relate to previous states in the sense of a memory. And that would mean that our Ohm's law, the proportional factor here, the resistance, depend in this example on charge. And that means it is no longer a linear law, it is a non-linear law. And that is illustrated here on the left by this kind of so-called curve of hysteresis. And this curve of hysteresis is nowadays a signature for the existence of possible candidates for this kind of memristors. And that is under construction and is analyzed in several research groups worldwide. I'm also engaged in such a research group in Germany, in Aachen, not on my home university, the Technical University of Munich. And anyway, in these research groups some years ago, the idea came up, we can do it better. Not with electrons and with electronical grids, but with photons. Because with photons, you calculate not with milliseconds, but with nanoseconds. And you can reduce significantly the energy consumption. So such photonic-based, for example, here is a number for concerning the energy consumption here, 75 watt, and that is rather close to the energy consumption of a living brain. I mentioned it with 20 watt. Now, this is a possible interaction of these technical neurons here. These are optoelectronic units, and the photons are realized by laser light, and the synapses, for example, there are different possibilities by Mach-Sender interferometer. You can observe that in these simplified neural networks there. There are the X neurons, that's the input, Y is the output, and then there is a layer between output and input representing the weights, and that is technically here represented by this Mach-Sender architecture. That means that it's a collection of mirrors which by shifting operations can realize or can simulate the synaptic interaction. Now I like that because in a popular way you can say it is a kind of brain of light. You are computing now with massless elements, but anyway, we have these two approaches here, memristic and photonic neuromorphic computing, which are able to reduce energy consumption for sustainable AI. Now, that is a nice perspective concerning all requests of sustainability nowadays and our energy problems. But in the end of a neuromorphic approach, I want to highlight another advantage of this approach, and that concerns, in a deep sense, mathematics and logic. And now I come back again to Turing. And you remember, I highlighted the undecidability of the halting problem of a Turing machine as a general limit of digital computing. And Turing came up with that in 1936, and actually it's only an example of a much deeper result in mathematical logic by Kurt Gödel in 1931. And that means, and that said that there exist definable but undecidable sets over the digits. For example, our halting problem, undecidable problem. 20 years later, by the way, in the picture, Kurt Gödel is here on the right. 20 years later, another great logician of the 20th century, the Polish mathematician Alfred Tarski, here on the left, came up with the result: if you consider real numbers, every definable set over the real numbers is decidable over the real numbers. And that means that analog computing with real numbers may overcome the limits of digital computing in the Turing-Gödel sense. That means the problems of mathematics, which are not solvable by digital computing. The philosophers are sometimes discussing, oh, there are general limits in thinking and so on. No, Turing and Gödel only restricted to digital computers, not general. If you extend it here to the real numbers, that means to analog computing, then you can solve all these problems. I think that is amazing. Now you can say, oh, that's nice for mathematicians, logicians like you, but what does it matter? It concerns, as we know, recently practical problems in medicine. And the idea is the following. It concerns medical imaging. You know that. CT and MRI and things like that. And the situation in a mathematical way is illustrated here in the picture. X is the object, for example, a tissue in the brain. And that is imaged. It is measured. An image is, mathematically speaking, a noisy measurement. And mathematically, that is expressed here by the y. The y depends, measurement, on a noise factor here, E. And A means some matrix considering the measuring instruments in a mathematical way expressed. Now the question is, the so-called inverse problem of measurement, the question is it possible to reconstruct, that is the arrow back, yeah? Reconstruction, is it possible to reconstruct from such a noisy measurement the original object with increasing accuracy? And that means by training neural network. Can we train a digital neural network with arbitrary accuracy to reconstruct the original object? Is that possible? And the answer is, in a rigorous way, very clearly no. It is not possible. And it depends on the undecidability problem of digital computing, which I mentioned before. Digital approximability with arbitrary accuracy is in principle not possible. Of course, you can do it in medicine to some degree, but you can also prove mathematically there is a lower bound of algorithmical accuracy with digital networks. But if you have analog algorithms, then in principle it is possible. And the point is, of course, that the neuromorphic computers may be nice candidates for analog computers. It was already mentioned this morning. And I think that is amazing from a theoretical point of view, mathematical point of view, but also from a practical point of view. Because medicine nowadays is improving its accuracy. It becomes more and more exact nowadays. And maybe today it's not so important and we are sufficient with these digital approximation. But what is in the future? And so I think to have this theoretical framework and discussing of the limits is, even from a practical point of view, very important. Now I like this photonic approach because it gives a link to another tool of computational procedures which I want to highlight in the end, namely quantum computing. You know, perhaps the photon can also be considered as a quantum system. At first, the photon can be used to realize the bits 0 or 1 by polarization, vertical and horizontal polarization to represent 0 and 1. But then main feature in quantum mechanics is a superposition. That means you can superpose both states, 0 and 1. That is here illustrated by this wave function, 0 and 1 in the brackets, and there are coefficients. They indicate how probable it is that in such a quantum state, the system is more in the state 0 or less in the state 1. That is a quantum bit. And the point is concerning quantum computing that you cannot only superpose 2 bits, but unbelievable many bits. That is illustrated here in the picture on the left in this package. That is a superposition of many bits. And in the first picture, you see a von Neumann architecture, and there every bit must be calculated one after the other, and that needs a lot of time and so on. And now in the quantum computer, you can apply a computational device to the whole package, and by that, an unbelievable acceleration of computational velocity is possible. That means that problems which cannot be solved in lifetime will be solvable in minutes or seconds. But it is not only a superposition. Here it is the application to AI. We can consider the Boltzmann machine. That means this neural network in statistical learning, which I mentioned before. And instead of the classical neurons, which are represented by bits, we can consider quantum neurons. That means quantum bits. And instead of the classical energy function in such a Boltzmann system, we can consider Hamiltonian operators. It is a kind of a translation of the classical statistical learning into the quantum formalism. And that means in the end practically an enormous acceleration for this optimization process. And here you see again the landscape with which I illustrated the optimization problems before. But in quantum mechanics, we do not only have the advantage of superposition, but also of quantum tunneling. And that is illustrated by the yellow arrow. Now in these networks, here in these landscapes, it is possible to penetrate the barrier of energy here. That means you have not go up to the mountain and then down, and so it shortened also the computational time. And it is amazing that the last Nobel Prize in physics was given to AI researchers again, which considered the application of this kind of quantum tunneling in the AI approach. And the last feature which I want to highlight is, of course, also philosophically very deeply. The so-called entanglement. It goes back to Einstein in 1935. This ingenious Einstein had the idea, or he observed in the quantum formalism, that locations in far distance can be in a common state, a quantum state, non-local. That seems to be that there is a kind of instantaneous reaction. And Einstein at first had the impression, oh, that is a contradiction to my constancy of light in the relativity theory. It is not, because it is a preparation in a common, non-local state. And that is the basis today of quantum communication. And I highlight that because it leads us to another complex system of the future, because this quantum communication is the basis of a quantum internet. That is illustrated here, how far distant locations are correlated here by satellites with photons. That means the light rays to both locations. And of course, this is under construction, but that leads us to communication with much more degrees of safety than the running communication systems today. Now, let's come to the end, challenges of complexity and hybrid AI. This picture should illustrate, I think, the both tendency, which I discussed here in my talk, and which we can observe in industry and science and everywhere. The red arrow is Moore's law, the development of Moore's law. You remember Moore's law, faster and smaller. It runs into limitations of miniaturization with nano and atomic scaling, and that leads to quantum computing. And therefore, I discussed it here so intensively. That is the red arrow. But the blue arrow, that is our analog tendency. That means more than Moore technologies, and with the neuromorphic computing and analog chips. And the future will be, perhaps you remember my picture with this brain of light, an integration of both here in the diagonal arrow illustrated. And so that leads us here to the future, I think, of computational centers. In the future, I think, perhaps already in the beginning state, a computational center will be an integration of all these approaches which I mentioned, because all these approaches has different advantages and different disadvantages. They are more or less appropriate for different problem-solving problems. Here, machine learning, physical AI, neuromorphic computing, quantum computing, and I think in the future it should be integrated in a hardware-independent AI, in the sense that scientists must not be aware of all these physical and mathematical backgrounds. You must remember the situation of John von Neumann. John von Neumann was an ingenious mathematician, and he had deep insight in electrical engineering. And to use this von Neumann computer in the early 50s needs all this knowledge. But in the future, in such a computer center, people must not be aware about the technology. If you use here your computer, you must not longer be aware of the electrotechnical machinery here. Only some specialists can do that. And that will be the future here. You can forget the insights of quantum physicists and electrical engineers and of computer scientists. You will use these instruments in medicine or elsewhere for concrete problem solving. And in some cases, you will use neuromorphic computing. In some cases, maybe appropriate the classical machine learning will be sufficient and so on. So I think that is a challenge, especially for the European research, this kind of integration. And what we therefore need for the future is, especially here in Europe, international standardization and certification of complex dynamical AI systems. I thank you for your attention.
Colloquium on Complexity and Chaos, Leon Chua's Pioneering Activity, by Professors Fernando Corinto, Politecnico di Torino, Ronald Tetzlaff, Technische Universität Dresden, and Professor Klaus Mainzer. We invite now Professor Fernando Corinto.
Dear colleagues, ladies and gentlemen, it's my distinguished pleasure to be in this magnificent building of the National and Capodistria University of Athens. I would like to thank the conference organizer for inviting me to this colloquium on complexity and chaos to celebrate the Professor Leon Chua pioneering activity on complex systems. And we are very close to the welcome reception, so I will try to be short. And I will highlight Professor Chua's activity on nonlinear circuits, and then my colleagues will go on other topics like cellular nonlinear networks and local activity. And for what concern Professor Chua's activity on nonlinear circuit and nonlinear dynamical systems, I have to say that it is very difficult to make a summary of Professor Chua's activity in less than 10 minutes. So I decided to have a different approach in preparing this presentation and to use picture because following a Chinese proverb, one picture is worth of 10,000 words. Or coming from Italy and relying on Italian culture, I would prefer to quote Leonardo da Vinci, a poet would be overcome by sleep and anger before expressing with words what a painter can do with an image. So, in illustrating Professor Chua's activity on circuit theory, I decided to base my presentation on covers taken from Professor Chua's books. And the first book is Linear and Nonlinear Circuits. And you can see the picture of the famous, there is no pointer, famous Chua's diode that is at the heart of local active circuits because it provides negative differential resistance. So a resistor that is able not to dissipate energy but to provide energy. It is the key essence of the local activity principle. And this activity, so Professor Chua developed this solid theory for nonlinear circuit, extending the theory of linear circuit by exploiting topological methods and state-space representation and energy-based principles. In particular, using the technical concept, graph theory, he was able to provide a systematic description of nonlinear circuits described by state equation. I mean ordinary differential equations. And this systematic approach allowed to Professor Chua to introduce a set of basic circuit elements that he collected in the circuit periodic table. And following this systematic approach, Professor Chua conceived the memorist, or already mentioned by Professor Mainzer in his talk, that is a short name for memory resistor. So memory resistor is just an element of a periodic table that includes several secret elements that are necessary for modeling many real devices, and I would say many real complex systems arising in biology, physics, and in many fields. So this systematic approach allows us also to develop a complete new field also for simulating and designing electronic circuits. And this holistic approach to nonlinear circuits has then been lead to the concept of nonlinear network theory that will be presented by my colleagues later on. And then Professor Chua introduced the concept of cellular neural nonlinear networks and cellular automata. To understand, to investigate the dynamics of these nonlinear networks described by circuits, Professor Chua developed several mathematical tools going from global local bifurcation analysis, unfolding theory, and it was mentioned in talk by Professor Asquith this morning, the unfolding principle for modeling nonlinear elements, and also the dynamic route map, that is a valuable tool for understanding the dynamics properties of the elements. All these solid theory permits to also develop a peculiar circuit, the so-called, the well-known Chua circuit, that is the first physical circuit that show chaotic behavior. And we are in a conference which is Chaos and Complexity Conference. So this circuit that make use of a few components, just two capacitor, one inductor, and one nonlinear element. The picture that I have shown before is the Chua diode, is the key element of the Chua circuit. So with less than $10, you can build in your lab this circuit, and you can experience chaotic behavior. So we have seen today many presentation and works based on the realization of digital version of these chaotic circuits. So, and also the well-known double score attractor is the fingerprint for this chaotic behavior. And this approach, this axiomatic approach to nonlinear circuit also led to the introduction of the local activity principle and the edge of chaos. And we have already seen, I will not go into the details about this principle because it will be presented later on by Professor Mantes, and that also we have seen his talk just now. And let me conclude with one of the last book done by Leon Chua. I'm co-author of this book, Nonlinear Circuit and System with Memoristor, in which basically we exploited his original systematic approach, and it was extended to circuits, including ideal memoristor. So basically, you can see that the original theory developed by Professor Chua the part in the blue circle, was extended also to circuit including ideal memoristor, and we developed the so-called flux charge analysis method that permitted to understand nonlinear dynamics in memoristor circuits, and also to introduce the novel concept of bifurcation without parameters. So this systematic approach is not only essential for the analysis, but also for the design. We can produce tunable chaos in nonlinear in the circuit with ideal memories. So here you can see a picture of a digital realization of tunable chaos in circuit with the memories. So to finish my presentation, I would say that this is not, of course, not a summary of Professor Chua's result, of a technical summary of Professor Chua's results on nonlinear circuit, but it's just a presentation to celebrate his next 20th birthday, that will be in less than 2 weeks. And in particular, try to present my activity, our activity in Torino with Professor Leo Chua, and we had the opportunity to work with him to share many ideas and discussion. And here you can see a picture. In the upper part, you see the picture during the Laurea Honoris Causa at the Polytechnic Torino in 2015. I had the privilege to give the laudatio of Professor Leon Chua for this Laurea Honoris Causa. And in the picture below, you see Professor Leon Chua with many friends also in this room, Professor Ascoli, and also Professor Ronald Tesla with other Italian colleagues, Professor Mauro Forti and Alberto Tesi, and we have this apple, so we become the Apple Boys, and this picture is taken during the conference, the Memories Conference held in Torino in 3 years ago, 2023. So thanks for your attention, and then the floor is.
Professor Roman Tetzlaff, the floor is yours.
So, ladies and gentlemen, it's my distinct pleasure to highlight another pioneering activity of Professor Leon Chua. You already heard, maybe you can start my presentation, that Leon was, let's say, a pioneering person in circuit theory. It has been mentioned in the talk of Fernando Corindo and Klaus Meinzer already. But let me come and tell you a story about another. Okay, it's working. Let me tell you a story about another episode of Leon Chua. In the late 90s, engineers are trained to linearize the mathematics of nonlinear elements. There have been many different nonlinear elements, and Leon Chua was looking on this confusion somehow and trying to categorize these different nonlinear elements in connection to basic circuit elements. So he developed the famous Chua quadrangle, which was published in his famous publication, The Missing Memoristor, the Missing Element, in 1971. He was connecting in his quadrangle basic quantities like voltage, current, flux, and charge, and showing the connection that you have a basic circuit element like the capacitor, a resistor, and inductor, and there was a missing link between charge and flux, so he introduced a hypothetical element which he called a memory resistor, a memristor. In that time, nobody knows anything about a memristor. So it's he defined it as a two-terminal element and developed a complete theory about this element, a memristor. The memristor, he classified a memristor as an element who has identical zero crossings when you are looking at voltage and current through the element, voltage at its terminals, and classified this as a fingerprint of a memristor, of passive memristors, and showed another fingerprint of the memristor, which we already saw in the presentation of Klaus Mainzer, that the memristor has a fingerprint of a pinched hysteresis loop. And when you drive the memristor with a periodic input, then with increasing frequency, the loop area of the pinched hysteresis loop is shrinking. This is a very typical behavior, and it was already classified in his first, let's say, treatment of the memristor. Later on, this fundamental property, building on this fundamental property, he published a second paper, which is called Memristive Devices and Systems. Leon Schur became aware that with the memristor definition, which he gave in 1971 in his paper, The Missing Circuit Element, he needed a generalization where he introduces the voltage in a Ohms-based law, state-based law, introducing a state X which can be higher dimensional, and the state X is describing a physical property of the device. It can be the temperature, it can be another quantity which is describing the physical state. And this state follows a nonlinear ordinary differential equation. This was the beginning, in principle, of a classification already in 1976 in his second famous publication. In that time, Leon Schur was not aware that an element, continuous dynamics, showing continuous dynamics, this was, want to go back. He was not aware that already in 1801, Sir Humphrey Davy, with his student assistant, was able, with Michael Faraday, to show and to experimentally the behavior which was proposed by Leon Schur in 1971 in a continuous arc lamp. So this, already in 1801, we see the behavior of a memristor, but people haven't been aware of this, that this, let's say, behavior can be classified to a memristor. In 1976, in his extension of the ideal memristor theory, he was not only able to show this more mathematical, let's say, generalization, which classifies, let's say, more realistic fabricated memristor devices in that time, but he can prove that the famous Hodgkin-Huxley model, where Hodgkin and Huxley received the Nobel Prize, has been contained two memristors for the sodium ion channel memristor. It's a second order memristor. And for the potassium ion channel, these variable resistors, where Hodgkin and Huxley haven't been aware of that, are memristors indeed. And this was a major contribution of Leon Schur in 1976. Later on, a lot of discussion starts about the classification of memristors, and in one of his, let's say, major contributions, he performed a classification scheme into ideal, generic, and extended memristors. The Hodgkin-Huxley memristors are generic memristors, can be classified in generic memristors, and mostly the fabricated devices can be classified in current control in extended memristors. This is a major contribution because independent of the special structure of a memristor device, of a memristor structure, this device can be classified according to the scheme of Leon Schuher, which he developed in 2014. When we are looking on the history of memristor devices, there have been only few publications, not so many. Leon Schuher continued to work on that topic until 2008, when Stanley Williams published his famous paper, The Missing Memristor Found. He was able to connect a fabricated device at Hewlett-Packard Labs to the theory of Leon Schuher. And this was a major breakthrough in the development of memristors. When you are looking, for example, on publications, you see, and we're starting with 1971, when we have the famous publication of Leon Schuher, where he introduced the memristor. And starting in 2008, we see an exponential increase in the number of publications and citations for the memristor, which is still increasing exponentially. The effects of his discovery in 1971 is ranging now and, controlling the next development of future technology. I can say that overlooking the activities, it's not only the publications that we can observe in these statistics, we can also see that meanwhile major semiconductor fabrication companies are producing memristor devices, so it's not only an academic game, it's real-world technology, and memristor technology will come to, let's say, household devices, to car manufacturing, car assistance systems. Infineon Technology is using memristors for creating spiking neural networks for neuromorphic structure. So Leon Schuher's pioneering activity ranges into the future, and we can say it will change the technology from transistors will exist, of course, but some of the circuits will be more efficient by replacing transistors with memristors. And coming to the last slide of my presentation, we already saw that Leon has published many excellent books. I would like to highlight these publications of Leon for those who would like to learn more about memristors. These are his tutorial papers. The first one, If It's Pinched, It's a Memristor. Everything you wish to know about memristors but afraid to ask. 5 non-volatile memristor enigma solved. And the last one, Memristors on the Edge of Chaos, Quo Vadis. These are major contributions of Leon, defining and classifying all kinds of memristors and relating memristors to real-world technology. Thank you very much.
And we invite now Professor Mainzer.
Yeah, it was very nice that Professor Teslav was the last one, because what I want at first to remark is my contact to Leon Schuher. And you invited me in 2002, I think, to a conference in Frankfurt, because Schuher knew my activities in complexity since the early 90s, and that was for me personally a highlight to get this contact. And later on, we had a lot of cooperations, and when I met him for the first time, I explained him my first academic love was not complexity, it was symmetry. And symmetry, in a sense, which also relates here to essence. I was, in the philosophy, very impressed by Plato. And Plato, you know, in one of his famous dialogues, had this ingenious idea that this universe is built on symmetries. In that time, it was the Pythagorean tradition, the Platonic bodies, but that was an immense influential idea. And in my book here on the left, I considered especially the concept of symmetries as a basic of a modern standard theory in physics for the universe, elementary particle physics. They, in a modern sense, also explained that the different elementary particles can be ordered by so-called symmetry groups, the gauge groups. Now, anyway, then typically for Leon Chua, he invited me and said, "Oh, write a book about symmetry and complexity." And that was a book, my first book in his series on nonlinear dynamics. And with that, a deep discussion started in TUM, my home university, and in Berkeley. And then I learned more about his, in some sense, philosophical ideas. The background of all these engineering activities. He's an engineer and computer scientist. But what we had in common is our love to mathematics. Mathematics is the general language, and that is not typical for European engineers. I know engineers very well. I have 2 children as engineers, and my father was an engineer, and the technical university is full of engineers. But this kind of approach of Chua, that means he had a deep mathematical understanding. And that because I'm not an engineer, my background is physics, mathematics, philosophy, things like that. And so there was a toy world, so to say, in which we could, or I could exemplify his approach. And these are the cellular automata. And without going into the details, I will roughly illustrating the cellular automata. The cellular automata is very simple. Everyone can understand what is cellular automata. Anyway, what is slow? We wrote a book about the universe as automata, from simplicity and symmetry to complexity. You have perhaps on the background of my remarks the impression that has something to do with this understanding in modern physics that our universe is based on symmetry. And now we want to illustrate it with the cellular automata, a simplified world of the so-called cellular automata instead of these complex elementary particles in the real world. And you will see that essential features of the physical real world can be illustrated in this toy world of cellular automata. Now, the systematic connection between complex dynamical systems and automata is easy to understand. If you have a dynamical system, it is determined by time-depending differential or difference equation, and if the continuous variables in this equation are replaced by discrete binary quantities, you get these functional schemes, which you see on the left, and that are in principle schemes of automata with feedback loops. And now in the 50s and in the 60s, the idea came up of great mathematicians and physicists of the 20th century, such as John von Neumann, that even life can be understood as automata. That's an old idea, you know, in history. René Descartes and all these people had this idea, and now it can be made precise. That was the idea of John von Neumann, a theory of self-reproducing automata. And here, that is an illustration. I will not go into detail. You see such a checkerboard, and in each cell there is a number which indicates the state of the system. And then by local rules, which are very simple, and every child can understand it in principle, you can do it by yourself and following these rules, and then you can get the self-reproducing organism, so to say here. And the amazing fact from a mathematical point of view is that these cellular automata are in a mathematical precise sense equivalent to these digital algorithms which I mentioned before, to a Turing machine, for example. So in some sense, that was the idea of John von Neumann. Such an automaton is an equivalence to a computer. And von Neumann wrote a famous book, The Computer and the Brain. The brain with its abilities of self-reproduction. And that in a precise sense can be illustrated by the automata, here in that picture. Now a very simple approach is not two-dimensional, is a plane developing like an organism, but line by line. That is sufficient to understand the complexity of the approach. That is shown here, first line, and the assumption that the state of a cell in the following line depends on the three preceding cells in the line above, the previous line. That is illustrated there. And then with two binary states, 0 and 1, or black or white, you get 2 to 3 cases. That means 8 cases. And that is, so to say, the code. If the black and white following cells are represented by 0 and 1, you get a binary code. The binary code for this kind of pattern formation. And there are, of course, cellular automata with very complex pattern, symmetric pattern, chaotic patterns, what so on. And there is this binary number, it's 0 and 1, and you know that can be translated into a decimal number. For example, here 110, and on the left you see the binary coding number. Now, in the end of the 90s, you know, the computer power was increasing. In the time of John von Neumann, you could only do that on a paper by yourself, this expansion of patterns, but now you had the computer, and the computer could produce amazing large patterns. And the idea of Stephen Wolfram, who was already mentioned, he was originally a physicist, but then he became a computer scientist and even an entrepreneur with an own company. He had the idea, let us classify the cellular automata, these complex patterns, in the sense of dynamical systems. And you know, in the theory of dynamical systems, there are equilibrium systems here on the left. That means after a few steps, the system will end into a final state and not change forever. That means on the left in black. And it will, in the beginning, there are some steps, but then no change. Then on the right, these periodic development in time, or these on the left below, this picture with these chaotic distribution of these triangles. And if you do experiments in the computer, the pattern depends on the tiny deviations of the initial state, and that reminds on the Lyapunov component, you know, where such tiny deviations can lead to completely different developments. Or on the right, you can even generate organic-like very complex structure. But actually, that is a quasi-experimental experiments with the computer. But Stephen Wolfram, he was originally a physicist. He proclaimed that will be the future. We will give up these Newton-style physics with equations and solving complex equations, and sometimes we cannot do it. We only can approximate with numerical mathematics. We will give up it because we will have so dramatically powerful computers. Only by very simple local interaction, it will generate all kinds of patterns and solutions. That was the ideology in that time. And then Leon Schuer and we came up and said, no, we defend the classical, mathematical, physical approach because we want to have, that's a word which Schuer liked, rigorous. We want rigorous results and not these quasi experimental approximation. And that was written down here in this book on which I mentioned before, The Universe as Automata. At first, one must define what, in a precise sense, what a cellular automaton is. That is illustrated here with the boundary conditions on the left in green of a ring, and then you see these cells. And the idea is that each state, as I mentioned before, depends on three previous states of cells, and by that you get truth functions which are systematized here in this truth table on the right. And these are 2 to 3 cases, so you get 8 cases which can geometrically, and that is now important, illustrated by a cube which you find on the left. And this is a concrete application to a rule, namely 110. You remember these cellular automata which I illustrated before. 110 is a decimal number which represent a certain binary number with 0 and 1, and these zeros and 1 are the coefficients of these 8 cases from the power laws of 2 to 7 down to 2 to 0. And if these coefficients are 0, then the corresponding edge in the Boolean cube on the left is blue, and if it is 1, then it is red. And so you get a typical geometrical structure that will become later on important for any cellular automata with these different colors. Now, in that sense, such a system can be understood as a dynamical system with 3 inputs and then a state equation and an output equation. Now the point is you want to use, or we want to use, all the advantages of the highly developed, in mathematics, highly developed differential equation in order to get rigorous results. And for that, the 0 and 1 is, by technical reasons, replaced by -1 and 1. And then the idea is that the truth table, which I mentioned before, is mapped onto a dynamical system in the physical sense, where the states evolve in real time via an ordinary differential equation. And the output, y, converges to a constant, either -1 or 1 at the equilibrium state. And in the cube, for that, at the edges, there are not the triples with 0 and 1, but with -1 and with 1. Now, I will not go here in all details, but the point is that in this way, you can characterize each cellular automaton with these conditions, 2 binary digits and these 8 cases, you get exactly 256 possible cellular automata. That is, so to say, our toy universe. And you can characterize each cellular automata of this kind by a scalar ordinary differential equation of the dynamics which I mentioned before. That is the scheme of this equation, and here it is illustrated. Below you found the patterns, such as in the Stephen Wolfram approach, with these 8 cases of each rule, and then the number of the rule as decimal number. But on the top of each example, you find the corresponding dynamical system represented by a difference equation. So each automaton, that is a message here, is a dynamical system in the physical sense. And you can treat it with all the methods which you know from the theory of complex dynamical systems. And here, an important example, the rule 110, I will not go into details. You see the typical pattern, which is generated, then the truth table, and then the typical cube with the typical colors of this cube here, and there the dynamical equation. Now, complexity here. In the edge of this table there, you find kappa, the Greek letter. Kappa is equal to 2. And that is a complexity degree. That means you remember that Wolfram had the idea to classify the complexity, but he did it in a very intuitive way by experiments. Now here in a rigorous way, namely the cube, which characterizes each cellular automata with its different colors, can be characterized by these kind of parallel planes which separate the different colors of the edges. And if you only need one table, then actually you can see it in the corresponding patterns. You have very simple cellular automata with simple patterns. If you have 2 parallel planes, then they are more complex. And the most complex examples are characterized by kappa equal to 3, namely by 3 parallel planes. So you have a complexity in the world. But then I cannot go here in the details. It is a little bit tricky. Symmetry. Symmetry in this world of 256 cellular automata. Now the point is the following. I mentioned it in the beginning. The cellular automata is very simple, but it is a representation also of deep computability results. By random, it was found that 110, this automaton, is a universal automaton. That means it is able to simulate all other kinds of automata. That's the same situation of the universal Turing machine, which is able to simulate all kinds of other Turing programs. And these kind of universal machines are actually our general purpose computer now, very powerful machines. And the question was, how many of these universal automata exist in this world? Now you can do it in the Wolfram sense by experiments and try to find them. Now we did it here in a in a rigorous way, in a mathematical way. Namely, these three other cellular automata with these numbers, which are illustrated here, are in a strict sense symmetrically equivalent. That means you can't find mappings or transformations to transform in a symmetric way the structure of cellular automata 110 in all the other three automata and vice versa. And the idea is, roughly speaking, that these transformation consider a relation between the patterns which are produced by the system step by step and the characterization, the symmetric properties of the cube. The cube is like an elementary particle, you know, and it has certain symmetric features because of the different colors. And that is a relation. These symmetry transformation here is a relation of that. Anyway, in the end, I called it the holy grail of this universe of automata. You can find a group, a symmetry group of transformations which are able to transform each of these universal automata in the other one. And that is a very simple group in mathematics, Klein's Vierer group. Anyway, it is the idea, now you understand my introducing remarks, the idea you have a world, you have a, so to say, a toy world for children, and the elements here are these kind of automata, and it is characterized, like our big universe, by a symmetry, fundamental symmetry group. And the idea that perhaps our universe can be described by automata, that was rather modern in the time of John von Neumann, and his great competitor in Germany was Konrad Zuse. I mentioned in the beginning Konrad Zuse came up with the technical computer some years earlier. There was always a competition, and Zuse in the same time, when independent from one another, when John von Neumann came up with this idea of cellular automata, Konrad Zuse also wrote a book on, the title was Calculating Space. But that is classical, and you know, nowadays we know very well that the laws of our universe is not classical. Physics, that was a great idea of Richard Feynman, and with his claim in 1982 that we should construct a computer which does not follow the classical physical rules, such our computers here is classical electrodynamics, but the quantum computer. And therefore, and then the idea came up that the cellular automata should also be extended to a quantum cellular automata. I will not go here into detail, but these two schemes illustrate what is the target of this kind of research. In the first blue block, you see our scheme, which I mentioned before, for a classical cellular automata with these three inputs. That means the two neighboring cells and the cell, and then the uniquely determined following cell, and following the Boolean table. And then the idea that the following state is not uniquely determined in the classical sense, but by a quantum probabilistic distribution or a quantum amplitude. So it is nothing else than the transformation of the classical approach now in the quantum formalism, and you can do that to some degree in a rigorous way, and you get global transition amplitudes which can be applied to all these configuration in the pattern generation. Now, as you know, coming back to Feynman, Feynman had an ingenious idea, namely that the real quantum world is so complex with all its differential equations, you should describe it by diagrams such as the electrical engineers. And that was a famous, the famous Feynman diagram, which you can illustrate the electron-positron annihilation and the generation process of the particle. On the left here, besides these cellular automata, you find the corresponding Feynman diagrams. And the idea came up that this is a classical geometrical description, the Feynman diagram, and that could be done as a generation by the classical cellular automata. And these are these pictures which you see here. That does not mean that these pictures are an illustration of what is going on in the quantum world. If you want to describe it in the quantum world, then you must use these quantum cellular automata. So in the end, that is my last slide, the idea is, and that is perhaps a kind of research program, how far can we go with these extended quantum cellular automata in order to simulate or to model the expansion of our world with automata. But anyway, I think it is a nice, as I said for several times, it is a nice world, perhaps for children, to illustrate the complexity and the symmetry of our universe, nevertheless with rigorous methods of cellular automata. Thank you.
Πέρας της τελετής έναρξης, end of the conference opening ceremony. Θα ακολουθήσει δεξίωση στο Πολιτιστικό Κέντρο Κωστής Παλαμάς του Πανεπιστημίου Αθηνών, Ακαδημία 48. A reception cocktail will follow at the Cultural Center of the University of Athens, Κωστής Παλαμάς Building, Ακαδημία Street 48. Σας ευχαριστούμε πολύ για την παρουσία σας. Thank you very much for your attention.
I would like only